Hello everyone. Today we will discuss solve a problem on designing a differential amplifier. Okay. So here you can see the question here. The question is design a differential amplifier with the current mirror load. Okay. You have to design it with the current mirror load with following specification. Okay. So the circuits so far what we have discussed earlier are with the resistive load during the characterization and all. So here the question is you have to design with the current mirror load with the following specification. Okay. So these are the specifications which has been given: the supply voltage 1.8, gain 40 decibels, the load capacitance 10 picofarad, ICMR, that is input common mode range, which is the DC supply voltage, and slew rate 5 volts per microsecond, and power which is should be less than 0.3 milliwatts, and gain bandwidth product as 5 megahertz. Okay. Other than that, you have a process conductance means process parameters, which is mu p cox as 60 microamps per volt square, mu n cox as 300 microamps per volt square, the threshold voltage of NMOS device as 0.45, the threshold voltage of PMOS device as 0.5 volts, and the channel length modulation for both NMOS and PMOS is 0.1 and 0.2 per volts respectively. Okay. And this is the transistor or the differential amplifier circuit, what you can see here, which we have to design. Okay. So basically design means we have to arrive at the aspect ratio of the transistor with the given specification. Okay. So here there is no fixed procedure to design the differential amplifier, right? So there are several methods which you can come across, but today we will discuss one of the way to design the differential amplifier with the given specification, right? So these are the transistors M1, M2, M3 and M4, and M5 is the tail current which carries the total current, and the current in this is decided by a current mirror again, which is given from a diode connected MOSFET, a current mirror. Okay. So this will consider as M6. So now to to brief about the specification, the supply voltage and the gain what we given here is basically a DC gain or low frequency gain. Okay. And the CL, that is the load capacitance, is basically the capacitance of the next stage if it is cascaded. So if there is any other stage which is cascaded with this circuit, this particular circuit, so the input capacitance of the next stage will be the load capacitance of this current stage. Okay. So this will be the fan out kind of specification for the current circuit, right? And other than this, this also includes the parasitic capacitance as well. Okay. So other than this, we have input common range, which is minimum 0.8 volt and the maximum 1.6 volts. Well, you see this is the DC supply what we give for the transistor to ensure that the transistor to be in the saturation region. Okay. So to bias this, that is the input common mode range, so the DC supply. And the slew rate is nothing but the rate of change of output voltage. Okay, the rate of change of output voltage, which is given as 5 volts per microsecond, and the power specification which is given as should be less than 0.3 milliwatt, and the gain bandwidth product should be greater than 5 megahertz. Fine. So here to find the aspect ratio of this transistors, so this is basically a symmetric circuits. We know, we have already discussed that what is the symmetric circuits. So which means the M1 is exactly mirror of M2 and M3 is exactly mirror of M4. Okay. So now to find the aspect ratio of M1 and M5, we make use of ICMR minimum. Okay, so using ICMR minimum, we can find out what is the aspect ratio of M1 and M5. Okay, so now by making use of ICMR maximum, we can find out the aspect ratio of M3 and M4. Fine. So using the maximum input common mode range, we will find out what is the aspect ratio of M3 and M1. Okay. So we can also find the aspect ratio of M1 and M2 by making use of gain bandwidth product. By making use of gain bandwidth product, we can find out what is the aspect ratio of M1 and M2. This is the procedure what we are going to follow for the today's discussion. Okay, and the load capacitance what is given, so I will show it here, which is connected to the output node, which is an input capacitance if it is cascaded, and also I told this the capacitance also includes the parasitic capacitance value as well. Okay, fine. So now to find out the aspect ratio, in order to find out the design procedure, first thing is we need to find what is the current flowing through this differential amplifier circuit. First we have to find out what is the maximum current. Okay, so the maximum current in this circuit can be find out by the given specification slew rate or by power. Okay, so here before this, again, how can we find out the aspect ratio of any transistor? So by the parameter what we have is the current equation. Okay, the current equation what we have, ID is 1 by 2 mu n COX W by L into VGS minus VT whole square, right? So this is the expression what we have to find out the aspect ratio. So if we can find out what is the current ID and what is the overdrive voltage, we can find out what is the aspect ratio of the transistor with the by knowing what is the current flowing through that, whereas this mu n COX are the process transconductance which has been given. Okay, so the first thing is we have to find out the current. So current, as I told, you can find out by making use of power or slew rate. Okay, so by power we know that P is equal to V into I. So P is 0.3 milliwatt and VDD is 1.8 volts. So your total current I will be, so 0.3 divided by 1.8 is approximately 1.16 milliamp. Okay, so whereas this is the total current which is used in this transistor, but this value is not fixed, because here the power is not a fixed value they have given it as the power should be less than 0.3 milliwatt. So the current should be less than this what you get. Okay, so the another method is to find out by making use of slew rate. Okay, so I will elaborate the steps. So step by step to find out what is the how to find the aspect ratio of each transistor. Okay, so now to step 1 is to calculate DC current from slew rate or power spec. Okay, so to find out from the slew rate, we have an expression slew rate as I naught by the load capacitance. So we have not discussed this expression, we will discuss it later. For time being, you consider this expression. The slew rate is the total current divided by the load capacitance. I naught is the total current. Okay, So by this you can find out what is I naught, which is equal to slew rate into the load capacitance. The slew rate given is 5 volts per micro, and into the load capacitance, which is 10 picofarad. So 5 into 10, you get around 50 micro, and this will be pico, you will be still with f with minus 6, 50 microamps. So this is the total current which is flowing through the circuit. So here this is the 50 microamps flowing through the circuit. So this will be shared across two, branches which is flowing through the M3, M1, and as well as M1, M4 and M2. Okay, so it will be equally shared, which is equal to 25 microamps in this branch and 25 microamps in this branch. Okay, so this total current, if we verify that what is the total power dissipated with this current, P is equal to V into I, 1.8 into 50 microamps, which is equal to 90 microamps, which is less than 0.16 milliamps, the total power dissipation. Okay, it should be less than that. So since it is less than this, we can consider 50 microamps as the maximum current which is used for the design purpose. Okay, so by this we have find out what is the current flowing through all the transistor M1, M2, M3 and M4, which are all equal to 25 microamps, right? So this is the first thing what we have find out. So the next thing what we have to find out is to find out what is the overdrive voltage, right? To find out what is the overdrive voltage. So now all the device current are known. Okay, so step 2 is to find out the overdrive voltage. Okay, so here in this we have discussed about finding out the aspect ratio using ICMR minus or ICMR plus. So we will make use of the ICMR plus and find out what is the aspect ratio of M3 and M1. We will look into this. I will redraw the circuit. So here this is M3 PMOS transistor and this is M1 NMOS transistor. Okay, and this is diode connected and this is VDD, right? And the input for this is ICMR plus, right? So it is ICMR plus what we are considering for this, right? So now for consider transistor M1. For M1 transistor to be in saturation region, for any transistor what we have discussed to be in saturation region, we discussed that the gate voltage should be greater by threshold voltage compared to your drain voltage. Okay, the gate voltage should be greater than the threshold voltage compared to your drain voltage to ensure that any transistor to be in the saturation region. So here for M1 the gate voltage is ICMR plus, which is equal to the drain voltage. The drain voltage here, I will take this drain voltage here as Vx. So Vx plus VTN. Okay, so we are supposed to find out what is this node voltage Vx. So Vx is ICMR plus minus VTN. Okay, so here in the previous you see the value of ICMR plus is how much? ICMR plus is 1.6 volt and VTN is 0.45. Okay, so considering this, ICMR plus is 1.6 volt, VTN is 0.45. this is your Vx. Okay, the drain voltage. So Vx should be equal to 1.15 volts. We can take Vx to be somewhat approximated to 1.2 volts. Okay, so this is the node voltage Vx. So now consider to find out aspect ratio of M3, say for example. Okay, so to find out the aspect ratio of M3, we know that what is the current flowing through that. We have to find out what is the overdrive voltage. Okay, so overdrive voltage, which is VDS or VSD for PMOS transistor, which is equal to Vs minus Vd, whereas Vs is, this is source terminal, which is VDD 1.8 minus the drain voltage is Vx, which is obtained to be as 1.2 volt. So your VSD for M3 you get it as 0.6 volt, right? So now we have current flowing through the M3, which is 25 microamps, and drain to source or the overdrive voltage of M3, which is 0.6 volt. Okay, so using the current equation I M3, and the current equation what I am using is actually a saturation current equation. Okay, so 1 by 2 mu p COX W by L into VDS minus VTP whole square, means whole square. Okay, so here the current IM3 is 25 microamps, 1 by 2, and here we have what this mu p as 60 microamps. So I will take here 60 microamps per whole square, W by L of M3 what we are calculating. VDS is nothing but VD minus VS minus VTP, which drain voltage is, the drain voltage is VDS, the drain voltage is nothing but your Vx, which is 1.2, and source voltage is supply voltage 1.8, 1.2 minus 1.8 minus the threshold voltage of the PMOS transistor, you get it as 0.5 volts PMOS transistor. So this is 0.5, so 1.2 okay, so you get it VSD. Okay, it is VSD, Vs minus Vd 1.8 minus 1.2, this is 0.1 whole square. Okay, W by L of M3, so this is 25 micro, 60 micro. So by solving this you will find out what is W by L of M3 as 83.3. which you can approximate it to 83. Okay, and the same will be the W by L of M4. Okay, so this is the aspect ratio for M3 and M4. Okay, so now to find out the aspect ratio of M3 and M4 is known, M1 and M2 using gain bandwidth product. Okay, so using gain bandwidth product, by making use of gain bandwidth product, so that I will take it in the next. So now step 3. Okay, so finding out, this is step 2 and now step 3. So to find out aspect ratio for M1 and M2 from gain bandwidth product. Okay, so the gain into bandwidth is basically what? The gain AV into bandwidth means basically the dominant pole of the system. Okay, since it is a symmetric circuit, the gain I will take it with respect to, by taking this half symmetric of this, considering only M3 and M1, okay, as a common source amplifier. So this I will connect it into ground for analyzing the, for this analysis. Okay, so in that case I will have the gain of common source amplifier with PMOS load M3 as G M1 and M3 into R01 parallel with R03. This is the gain. Okay, and the dominant pole is 1 upon 2 pi RC. Okay, whereas the resistance R is nothing but the output resistance, and the capacitance is nothing but the output capacitance. Okay, so the output resistance of this this amplifier is nothing but R01 parallel with R02. So I will write it as GM1 M3 into R01 parallel with R03 multiplied by 1 by 2 pi. R is nothing but output impedance, which is R01 parallel with R03 multiplied by the output capacitance is the load capacitance, which includes parasitic as well as the input capacitance of the next stage, right? So in this and this will cancel, so your gain bandwidth product will be GM1 and M3 divided by, so the GM of M1 or M3 it is, okay, sorry, GM1, only GM1 we will consider. Okay, it's not M3, considering it for the symmetric. Or you can consider it with respect to M2. Okay, M2, because it is symmetric discussion with respect to this amplifier as well as M2. It is GM1 or GM2. Okay, it is GM1 or GM2. GM1 or GM2 divided by 2 pi into CL. Okay, so your GM1 or M2 will be equal to gain bandwidth product into 2 pi CL. Gain bandwidth product given is, it should be greater than 5 megahertz into 2 pi into CL is 10 picofarad. Okay, so is 10 picofarad. So solving this 5 megahertz pico 10 power minus 12 mega 10 power plus 6, you will get around 314 microamps per volt. So your transconductance of M1 or M2 will be equal to 314 microamps per volt square. And also we know that what is the current flowing through the M1 or drain current of M2, which is equal to 25 microamps. We can find out using the same current expression or the expression of transconductance in terms, we can find out what is the aspect ratio. So using this GM is equal to 2 ID into mu n COX W by L in the square root. Okay, so this is for transistor 1 or 2, ID 1 or 2, this is also 1 or 2. So substituting GM and ID and mu n, which is already given, you can find out what is W by L. W by L of 1 or 2, which you will get it as 6.57, or you can approximate it to 7. Okay, so this is how you find out the aspect ratio of M1 and M2. Okay, so we have find out what is the aspect ratio of M3, M4 and M1 and M2. M1 and M2. Okay, so only left is by aspect ratio of M5. We have to find out the aspect ratio of M5. So in this you can find out the aspect ratio of M5 by making use of ICMR minus. So I will take this part of the circuit for the discussion further. So now it is step 4 to get aspect ratio of M5 from ICMR minus. So the circuit, what you get is okay. So this is ICMR minus. Okay, this is M1 and this is M5. Okay, and here in the previous discussion we find that the input for the transistor M1, so that to ensure the transistor M1 to be in the saturation region, right, and the same thing, right, so that is the gate voltage should be greater by threshold voltage compared to your drain voltage. Okay, so this applying for the transistor M1. Okay, so the gate voltage, that is ICMR, for M1 to be in saturation region, ICMR minus gate voltage should be equal to the drain voltage plus the drain voltage. I mean, this we have discussed, I think not. This is one of the condition. The ICMR minus is nothing but, so this VGS, yeah, this VGS plus this VDSAT of this transistor. This ICMR should be VGS1 plus VDSAT of fifth transistor, right? So this we have discussed in the previous discussion. When we are discussing the DC analysis of DC analysis of differential amplifier, right. So, this we have discussed it. So, this input common mode to ensure the transistor M1 to be in the saturation region. So, the minimum value VICM should be equal to VGS1 plus VDS of this transistor, this we have discussed it, right. So, in the DC analysis. So, with this we have taken this expression, which is VICM input common mode minus should be equal to VGS of this M1 transistor plus VDS of M3 transistor, right. So, with that we have taken ICMR minus is equal to VGS1 plus VDS sat of 5th transistor here, okay. So, we know that ICMR minimum value is 0.8 volts, which is given. So, now to find out what is the value of VGS, to find out the value of VGS, we have the current equation for transistor ID 1 by 2 mu n COX W by L into VGS minus VT. So, corresponding to the transistor 1 whole square. In this I will take the expression of VGS1, which is equal to VT plus 2ID by mu n COX W by L of 1. This is about the transistor M1 in the square root, okay. So, substituting the threshold voltage of NMOS transistor, which is 0.45, ID 25 micro, mu n COX 60 microamps per volt square, W by L of M1 is known, W by L of M1 is 7. So, substituting all this we will get VGS1. We get VGS1 as approximately 0.56 volts, I think, which you can approximate it as 0.6 volt, okay. So, substituting in this expression we have 0.8 is equal to VGS1 is the same 0.6 plus VDS of transistor 5, okay. So, now VDS saturation of 5. So, VDS of 5 is equal to 0.8 minus 0.6, which is 0.2 volt. So, now we know the VDS of 5th transistor is 0.2 volt and ID of 5th is the maximum current, it is the tail current, which is 50 microamps. So, using this, the current equation for the transistor M5 and rearranging the current equation for the transistor of M5, you can find out W by L of M5 to be 2ID5 divided by mu n COX VDS of 5 whole square, rearranging the same current equation. So, ID is 50 microamps, mu n is 60 microamps per volt square, VDS is 0.2 what we get, and solving this you will get around 8.3, which you can approximate it to 9, okay. So, by this we have designed the entire circuit, that is we have designed the aspect ratio of all the transistor. So, this M6 is the current mirror. So, depending upon the current you want, you can adjust the value of M6 and M5 accordingly, okay. So, here we have find out the value of transistor M3 and M4, which is the PMOS transistor. The size of this is 83. The M1 and M2 NMOS transistor, which is 7, and M5 the tail current, which is 9, and M6 you can vary it accordingly with respect to M5 depending upon how much the current you want. So, this is the aspect ratio. By fixing the value of L for particular value, so the W of the each transistor you can find out according to this aspect ratio. Okay, and this is the design for the differential amplifier, right.